the galaxies, and it just acts as a big lens that bends the light, just as Einstein predicted. And so you can take images, and this is a very famous advanced camera image of a cluster called Abell 1689, and this one just is so rich when you really need to get a microscope and go over the photograph. There are so many these wisps of lens galaxies in here. And the really nice thing about this technique is once you've found 2 or 3, you can start to predict where these lensed objects might appear. And my colleagues have actually found 70 lensed objects in this field in addition to the long wisps, and confirmed a good number of them using spectroscopy. But this one back here is very interesting. This looks very unremarkable here when you look at it at that magnification. But it turns out, again, if you look in the visible, you don't see anything. But there is actually a very distant galaxy here that's been lensed by that cluster of galaxies, and this is what it looks like in the infrared. So these are the techniques that we'll use with JWST, and they will allow us to go all the way back to the very first objects. What we'll also be able to do is study how these objects evolve over time. This is a galaxy that's it's an infrared picture by Spitzer, and all the red areas just show populations of old stars. And on the right here, you can see some pictures taken again from the ultra-deep field that just show how galaxies look at different ages after the Big Bang. So this is that very distant object I mentioned about 1 billion years after the Big Bang. And if you look at older objects, you see they don't look like your sort of nice, perfectly formed galaxy here. There's a lot of irregular galaxies. There's a lot of collisions going on. So we want to understand, as time goes by, how these galaxies evolve, how they come together and start to form these kind of structures. So the assembly of galaxies is another subject that we'll be able to study and form ideas about as we collect the same images that we collect to look for these first light objects. And then the other 2 themes move closer to home. And the other big thing that you can do with infrared astronomy is you can look through dust. You can pierce, big clouds of dust and understand what's going on inside them. So one of the very famous early Hubble images is the Eagle Nebula. This is M16. And people were absolutely thrilled to find what they call these stellar nurseries just at the top here, where they could start looking for stars being born in these dark clouds. But as you can see, you can only really look at the edges where these things are visible in visible light. If you look in the infrared, lo and behold, suddenly you can see a lot more of these stars, and as you go to longer wavelengths, you can see more. So once we can pierce these big clouds of material where stars form, we can really start to study those stars and understand how stars form, what are the processes by which they form, actually do real physical measurements of them. And then we can also start to understand how planetary systems form around those stars and what are the conditions for that to happen. And this background picture is the Orion Nebula, and these are objects called propylids, and basically what you see in these images are a central star, and then this dark area is a disk, and you're seeing, in this case, the disk goes right across the star, so it has that sort of hamburger look to it. And then down here you see some more propylids, but these ones are actually being ablated or burnt off by the fact that they're very close to a hot star in this area. So we'll be able to really start to peer into these objects and see what's inside them, how they work, and we'll have the sharp enough images we can actually start to see structures in these objects. This is one that Hubble has done, and we'll be able to do the same thing for a much larger sample rather than just cherry-picking 1 or 2 that just happen to be in the right place and close enough for us to see. So we can really start taking the wrapper off the Orion Nebula and places like it where stars are born and understand how that process works and what's needed to make it happen. And as I said, we can study how planetary systems form. And then finally, the last theme is planetary systems and the origin of life. And we can do a number of things here, and I'm going to spend some time talking about this. But they both play to an important area of science that's growing in astronomy called the study of exoplanets or planets in other solar systems. And what we're trying to do with JWST is try to get some physical measurements of the atmospheres of planets. And then we're also trying to study these things here, which are called debris disks. So in the latter stages of planetary system formation, planets have formed and cleared away most of the gas and dust in these systems, and you're left with a cloud of debris, and I'll come back to this in a minute and explain. But why are people interested in exoplanets? Well, there's a very large growing field in astronomy, and a lot of the young people coming into astronomy are wanting to work in this area. In the last 10 years or more, we've discovered something like 309 exoplanets. And I put this web page up. The day I did this, it was 309. It's growing, day by day. You can check this web page and see what the current count is. But, that's a pretty amazing statistic. We already know that there are 309 other planets out there. And as yet, we haven't been able to take pictures of them, but we know they're there from measurements of the wiggle that they put into the spectra of, from the wiggle they induce, and by doing Doppler spectroscopy, we can get estimates of their properties. We can also look for these things indirectly by looking for their footprints, if you like, the mess they leave and the influence they have on dust in other solar systems by analogy with what they do in our own solar system. So there's a number of ways that we can do this with JWST. And then finally, there's a new technique that's been very popular since the year 2000 and is producing most of the new results we know about the characteristics of planets right now, called transit imaging. So I just put this up as a kind of quick explanation of where planets come from. So we think that planets start as clouds of dust and gas that collapse under gravity. At about 100,000 years, they look like those propylids I was telling you about. And you have a disk of gas and dust and a new star. And then by the time we get to about 10 mega years, we think planets have started to form, and they're removing most of that gas and dust from the system, and you start to have what's called debris left. And then at about 1 billion years, you have a fully formed solar system, much the same as our own solar system. So let me take a minute to talk about the debris. This is what our own solar system looks like. It's two different views. The view on the left with the yellow fuzz shows the inner solar system. The outer orbit there is Jupiter. And then these orbits are Mars, Earth, Venus. And in between Mars and Jupiter, there's this big disk of dust that's called the zodiacal dust disk. And if you can find a very dark site, you can actually see it. And this is a picture my friend Paul Callis took with an ordinary camera up on the volcano at Mauna Kea. So just there you have one big cloud of debris that's left over from the formation of the planets in our own solar system. And then there's also another one beyond the orbit of Neptune called the Kuiper Belt. And this is the same figure, except now we're looking at the outer planets. The blue orbit there is Neptune. And outside of Neptune, there's a lot of very large bodies. One of them is now Pluto, which we used to call a planet. But there's lots of other objects out there. Some of them are the size of Pluto. I think there's a couple bigger. And they form, a big belt of dust and, larger pieces of dust called the Kuiper Belt. And a number of people started to realize that our planets actually leave a footprint in that dust. So if you were in another solar system looking back at Earth, you'd find it very hard to see the planets, but you'd certainly see that dust if you had a camera sensitive enough. And this is a model that a couple of guys did in 1999 called Liu and Zook. And what you're seeing here is their model of the Kuiper Belt, and this is Neptune. And they predicted that if you were in another solar system looking back, you would actually be able to see the effect of Neptune on the Kuiper Belt. And if you kept coming back and looking again, you would see that change. So that's an interesting result, because what it tells us is if we look at debris in other solar systems, we can predict that there are planets there from seeing the debris in those solar systems, if it exists, changing. And it turns out also that a number of systems do have this debris, and the debris is being continually replenished by collisions. And even in our own solar system, there's a lot of collisions here producing dust, and likewise out in the Kuiper Belt. And the Jet Propulsion Lab did this very nice schematic here, which just gives you that sort of feeling of chaos and collisions and violence in the outer solar system. So we've been able to start looking for these dust signatures with HST and try to get images of them, and it's very hard. It really pushes the limit of what you can do with HST because these objects are very faint and they're next to very bright stars. So you have to find a way, pretty much like I'm blocking the light from that spotlight with my thumb so I can see what's around it. And we have special cameras called coronagraphs that block out the light from the star, and then we can look in the region around that star. And this is the kind of thing that we find. This is what I call HST's legacy. Most of these were taken with advanced camera. And this is a dust disk around a solar system that has the same kind of star as our sun. Some of these things are very asymmetric. Some of them are nice rings. This is a nice ring. There's another one here. This is a disk seen edge on. And the one thing that we see in all of these systems when we start to study them is they show a lot of evidence of planets being present in these systems. You know, they're asymmetric, they have bumps, they have warps, they have clumps in the dust. And these are all things that the theorists predict we will see as planets go around and they shepherd and dynamically sculpt that debris in the system. And so this is kind of what I'm talking about. This is, I think, one of the best examples we have right now. So Fomalhaut is one of the brightest stars in the southern hemisphere. And this is a dust disk, or dust ring, actually, around Fomalhaut. And the image looks very kind of mucky because we had to remove the light from that central bright star, Fomalhaut. And once we'd done that, we were able to see this ring underneath. And this is an HST observation. And this is a ring very similar to our own Kuiper belt. It's a lot further out. It's about 3 times further out than our own Kuiper belt. But nonetheless, it's a very analogous structure. And what we found when we looked at this in more detail is that the ring, or the center of that ring, does not correspond to the center that Fomalhaut sits at. So if you can imagine it, Fomalhaut is here. If it was at the center of the ring, you'd expect it to be there. And what this tells us is that there's a planet somewhere in this system on a very asymmetric orbit. It's not circular. And it's going round in this asymmetric orbit, forcing the dust into this offset ring, which is offset from the center of the star. And furthermore, you can see this ring has a nice sharp inner edge. And that's because the planet is also, sculpting the inside edge of this ring very much the way that Neptune does in our own solar system. So here we have, with Hubble, a disk system, a debris disk, where we can infer that there's a planet. And so what we would be able to do with JWST, which I put here, and I'm afraid the micron signs have popped out here for some reason. But with JWST, we can image that ring, and then we can actually start to image the planets, which are still young enough that they have their own emission within this ring. And just for comparison, I gave you a picture of the Spitzer image here. And this is the reason why we need that big mirror with those sharp images, because Spitzer can see there's emission from a warmer dust component, which we've colored green here, but it just can't resolve it. What JWST will be able to do is resolve all the dust components in this system, and it will be able to image the planets. So that's why we're doing this. And then I mentioned transiting exoplanets. This is another area that's extremely exciting. And this is one of those subjects that astronomers, I guess, one of my bosses called it a Homer Simpson moment. Those of you who watch Homer Simpson will know what I mean. But this technique was first proposed by Otto Struve in the 50s. And it wasn't until 2000 that we really started to be able to do this. And, probably there have been a number of objects we could have looked at for a very long time, and nobody had actually gone and tried to do this. And so the technique is very simple. It just says if you have a planet that's properly aligned with respect to the inclination that you're looking at it, that goes across the face of the star, and then you look at the light coming from that star, you will see a dip as the planet goes across the star. Now, it's not a very big dip. Jupiter, if you were looking at the right orientation of our own solar system, Jupiter will cause a 1% dip in the light from our sun. And we on Earth would cause a 0.01% dip, which is a lot harder to measure. But 1% is